going to move on in Chapter 2 to Lesson 2.2 on evaluating and graphing polynomial functions. So let's go over some vocabulary. First off, a polynomial is a monomial or a sum of monomials. If you look on page 95 in your textbook, you'll see a chart that is labeled common polynomial functions. So a monomial is a single term, and a polynomial is if you have more than one. A polynomial function is then in the form f of x is equal to, or h of x, or any other variable of x, equal to a sum of monomials. When we write our function in standard form, it needs to be in order of least to greatest of exponents. And then the very first term would have the leading coefficient. And whatever degree is at the front of the pack would be our degree for the term. And then the very last number that doesn't have any sort of variable attached, of course, is our constant term. So let's take a look at some of the examples on how we can determine if something is a polynomial function, and if it is, what order does it need to be written in, what degree is it, what type is it, and what is the leading coefficient. So our first example is h of x is equal to x to the fourth minus 1/4 x squared plus 3. So yes, this is a polynomial function. It's already in standard form because the order of exponents is decreasing from 4 to 2 to 0. It has a degree 4, so it is a quartic polynomial function. So of course we know that a degree of 1, so just a plain x, would be a linear equation. Then squared, x squared would be quadratic. We just had an entire chapter of that. X to the third would be cubic, x to the fourth would be quartic, and anything greater than that, we really don't have a shortcut name for it. And then the leading coefficient is 1. It's the coefficient that's associated with x to the fourth. All right, next example. All right, this does appear to be a polynomial function, but we need to rewrite it in the proper order. Pi x squared needs to be at the front, plus 7x minus the square root of 3. So it is a polynomial function, rewritten that way. And then it is squared, so it is a quadratic function, so it has a degree of 2 and a leading coefficient of pi, 3.14159, something, something, something. Example 2, this is not a polynomial function because of that negative exponent. We need to have positive whole number exponents for our polynomial functions. So negative exponents means that it is not a polynomial function. And then for part D, this is also not a polynomial function because the term 2 to the x power does not have a variable for its base, and it has an exponent that is and does not have an exponent that is a whole number. It has a variable. All right, example 2, evaluating our polynomial functions by direct substitution. So direct substitution is exactly what we've always done with these problems. We're given a function and we're given a value of x, and all we do is substitute it in and solve it. So write the original function, substitute 3 for x, and then evaluate the powers and multiply, so order of operations, then simplify by adding and subtracting. And finally, our answer is 23. So what we've always done, pretty easy. Example 3 is where we get into synthetic substitution. This is another way to evaluate a polynomial function. This method, as we're going to see in this example, involves fewer operations than what we did in direct substitution. And once you learn it, it's actually pretty easy to do. So let's take a look at this function. We have 2x to the fourth. I apologize for the typo on the exponents. It's supposed to be 2x to the fourth minus 5x to the third minus 4x plus 8. And we want to evaluate it for x equaling 3. So first thing we're going to do is we're going to write the coefficients of the function in order of the descending exponents. And then write the value for which we're evaluating the function to the left. Now notice that there's a 0 in there to represent the x squared. We went 2x to the fourth minus 5x to the third minus 4x. We skipped over x squared, so we need to put the coefficient of 0 as a placeholder. Then what we're going to do is we're going to bring down the leading coefficient, so follow the blue arrow, multiply that leading coefficient by the x value, so 2 times 3, write the product under the second coefficient, so again, follow the red arrow, and then we're going to add -5 plus 6 to get +1. And they're going to repeat this process. So multiply the previous sum by the x value, write the product under the third coefficient, add, repeat for all the remaining coefficients. So that looks like this. The final sum is the value of the function at the given x value. So we're going up and down, up and down, up and down, all the way across until we get the value of 23. All right. Before we go on to example, well, technically example 5, because I'm skipping example 4, since we don't really have to worry about standardized tests too much in Korea. Yay. I want you to look at page 97 in your textbook discussing end behavior. This chart is going to be very important for helping simplify what we do with polynomial functions and getting an idea of what the graph should look like before we continue with graphing. So please take a moment, pause this video as long as necessary to look at your textbook at page 97. When you're ready, go ahead and press play to move on to example 4, technically example 5. All right, so graphing polynomial functions. When we graph polynomial functions, it's very similar to what we've done in the past. All right, so we have 2 examples here. Let's take a look at the first one. -x to the third power plus x squared plus 3x minus 3. So we're graphing a cubic function. Now, when we graph the function, you want to create a value, so a table of values, and I've seen several of you use this technique when you're graphing your quadratic equations. So you're going to continue with that for your polynomial functions. So you're going to graph, you're going to make the table, and whatever the corresponding points come from that, you're going to plot them and then connect the points with a curve, and then double check that the end behavior matches what we expected it to do. So when we look at the end behavior back on page 97, if I have an odd degree for my polynomial, my graphs are going to go in opposite directions. As x becomes greater, we notice that y value becomes negative, goes towards negative infinity, and as x becomes more negative infinity, the y value goes up and becomes more towards positive infinity. So end functions give us an idea of what this graph should look like. All right, so there's our end behavior as we see. The degree is odd, the leading coefficient is negative, so it's going in opposite directions, and opposite of whatever x is, the y is going to have the opposite response. All right, so now we're going to take a look at the second function, which we no longer have the function for, so let me repeat it for you. The graph was f of x is equal to x to the fourth minus x to the third minus 4x squared plus 4. So again, make our table, pick a few points to go with. With quadratic equations, I used 5 points, but with polynomial functions, just like the textbook recommends, I suggest using at least 7 points. You're going to have a lot of twists and turns, and you want to be able to accurately show that in your graph. So once you've made your table of values, you're going to plot those points and then connect the points with the smooth curve. Now notice that because we have an even degree and the leading coefficient is positive, that our graph all points up. And if it were negative, then both ends would point down. So that gives us an idea about what to expect on the end behavior. All right, let's take a look at a word problem and see how we would use our polynomial functions in a word problem. So the energy E in foot-pounds in each square foot of a wave is given by the model E is equal to 0.0029 s to the fourth, where s is the wind speed in knots. Graph the model. Use the graph to estimate the wind speed needed to generate a wave with 1,000 foot-pounds of energy per square foot. So step one, of course, is we are going to make a table of values, and then we are going to graph them. Now this is something that is going to the fourth power, so you would expect a few twists and turns, but we're only concerned with positive values because we want positive speeds. So plug in positive speeds for knots, and we have 0, 10, 20, 30, 40, and we can see corresponding parts. And then we notice that between 20 and 30, that's where it goes from 464 jumping up to 2,349. All right, then we want to evaluate the graph. So we've graphed it, and we want to evaluate the graph to see when S is approximately 24. And you can use your tracing feature on your calculator to help see as X moves closer and closer between 20 and 30, at what point does Y become closer to 1,000. So our tracing feature in our graphing calculator will help simplify that process quite a bit for us. So the wind speed needed to generate the wave is about 24 knots. So lots of wind speed creates more exciting waves. And that's it for lesson 2.2 on polynomial functions. Please make a note of whatever questions you have so that we can address them in class. See you next time.